start with from the very simple example, which is I will take you back to the past, to our first learning journey. So all of us started learning from the very first activity books, where the main activity was just to trace the line while connecting the dots here, for example. And after that, we obtained the contour, which represents the edge, or this line that represents the object. And then the object itself, in this case, which is the colored apple. So in this case, so for the fruits, we can have, for example, for animals, so this is a cat. And like this, we started learning things around. So we started learning the objects of this word based on this like representation given the contour information. So these examples are extracted from these activity books, but our learning experience extends to the real world, where, for example, if I show you this, you may guess, what is this? So, for example, it's a giraffe, this is a hand, so I will let you think, what is this? Seems difficult task, but okay, this is a car. And for example, you can, from this, you understand, this is, for example, what? It's a man and a woman crossing the street, for example. So I would like just to highlight the importance of this contour information, but the representation, as you know, here it's a continuous line, but in the reality, we do need that dot-to-dot representation, or let me say the description of contour given a set of dots. So I will take this example, very simple example of the shapes. We have the square here, for example, this is the contour of a square. Here, square is represented with the number of points, I don't know, 100, 200, 300, you can decide this number. But after all, if you can see, there are 4 main points. If, for example, you have these 4 main points, you can decide and say, yeah, this is a square, I can recognize this. So these points that are the ones having the, let me say, the most important to describe the shape are called descriptors. And so I'm doing all this just to tell you that, okay, we are learning, we are starting from here. And this may take us also to another like research topic, which is not only we are describing a shape. This description can also take you to the shape classification task, which is like based on these contours. I can say these are fruits, these are like animals, and so on. So today, the paper that I am sharing with you, it's about shape, or let me say contour classification. And so we can see that the input is contour, a representation with a set of dots. We are going to discuss that later. And we have a classification algorithm. This classification algorithm, we are going to explore it together. And after all, given the input, it's gonna decide the output. It will say, it will tell you, okay, this is a cat, got it. Or it's if it's something else, like for example, a dog or whatever. So I wish that until now it's clear what we are going to discuss today. Okay, please let me know if all is okay, or you can interact, you can ask me questions for each slide. I don't mind that. Yeah. Hello. Okay. If something is not clear, just let me know, please. Okay, so here we go. Before diving into our paper, I just want to highlight or mention the importance of this research, because if we are working on contour data classification, it can help in a lot of real world scenarios, such as, for example, in the case of biometric security systems, it can assist for skin cancer classification and leaf classification as well, and many other topics. So Now, before also diving into our paper, I want just to make sure that we understand the paper from the title. And this is mainly in most of your research papers that you may see. Always the title, it gives you clear information what the paper is going to be about. So the title here is DeepGCSS, a robust and explainable contour classifier, providing generalized curvature scale space features. I may give you 2 minutes to think about the main 2 keywords of this in this title. So the word deep is from deep learning, and robust is also related to deep learning. Explainable, again, deep learning. Contour, it's related to contour data, contour information. And GCSS, which is providing generalized curvature scale space features. So it's related to contour representation. And so it's a deep learning classifier. So from here, from this title, the main 2 words, so it's a generic approach. We are studying it in the case of this paper, but whatever paper you can understand from the title. So if we are like guessing about contours, there are like different problems related to contour. If I have an image like this, for example, this is an image representing square. How to extract contour information from an image? It's a question to be answered. And what pre-treatment shall I do to get a set of points? How many points? And so on. And among these points, how to choose the most important points that are going to be like from these points that I'm going to be able to reconstruct the input, which is the square in this case. So here you can see the answer in the title is the GCSS, standing for the Generalized Curvature Scale Space. So this is a contour descriptor that we can explore it later. And next we have the word classifier. So when it comes to the classification, we are already mentioning that we will use deep learning classifiers, and I was saying so far that it's mainly designed for image classification. And for this, I want you just to take a look on the way that we embed image data to feed to machine learning classifier in general and neural network in particular. So an image is always in most of the cases represented as a matrix, because as you know, in image we have it's represented with the different pixels. If it depends, you have, for example, binary image, like in this case, it's a set of white and black images, or you may have grayscale image or RGB or so on. So in this case, for example, we will have a set of metrics of numbers 0 and 1. If, for example, let me say for black, we give the value 1, or for white, the value 0. So you can have this as a matrix. It's a representation of the contour, of the image, excuse me. But when it comes to contour data, also we can have a matrix, and we can see that as an image, okay? But in this case, when we want to compare image to contour from like embedding point of view, we can say that if I have a contour, I can see it in the Cartesian plan. For example, I would have my x axis here, my y-axis here, and I may have coordinates, Cartesian coordinates or Euclidean coordinates of each point. For example, this one it's 1, 1, this one it's 4, 1, and so on. And after that, I am going to like store this set of coordinates in not a matrix, it's a vector here, and I may have one like column for the x coordinates and the other for the y coordinates. Still, it's a problem because here I am saving 1, then 1, 1, then 4, 1, then 4, 4, then 1, 4 coordinates, but I don't know which order must be, which is the starting point. So all this is a problem that we may see in this paper, how it's going to be treated. But we move to the second keyword, which is the classifier. So here we have a deep learning classifier, and from the title we can find a robust and explainable. So we have mainly 2 topics going to be treated, which are the robustness and the explainability of the deep learning architecture. And as I took this table from the state of the art to show you a set of CNN convolutional neural network architecture, which are examples of deep learning architectures. For example, LeNet, we have AlexNet, and so on. But what I wanted to show in this table is that all of them, I would say, are designed for image data classification, which, as we have seen so far, extremely different from the way we classify contour data. And the second thing, as you can see here, the metric to measure the performance of the CNN model is the error rate, which is through years. It's going to be decreasing, and the number of parameters which is increasing, which is justified by the fact that we have access to resources, workstations, servers, and so on. From hardware point of view, we have no problems, and here for sure all this is helping to increase the accuracy, which means that we decrease the error rate. But also, at some point, we keep increasing the number of parameters that may have a problem at some point. So if we can catch now the few problems from the title, we have problem related to contour description. We have a problem related to robustness and explainability of deep learning models in general. We have another problem related to deep learning models are mainly designed for image classification, how to adapt that for contour data. And also deep learning techniques, let me say, are having a problem when it comes to the huge number of parameters. So what we will do now, we are going to try to answer this set of questions or to address this gap in the literature. But before that, we may dive into the state of the art that is going to be divided mainly in two parts. First one is where we are going to take a look on the existing contour descriptors, and the second part when it comes to deep contour classifiers. Here we will focus on deep learning techniques. So for descriptors, if you were trying to read the second section in this paper, which is the related works, I'm going to summarize this now. Authors were discussing the types of descriptors existing in the literature, which are global descriptors and local ones. For global descriptors, they were focusing mainly on region-based descriptors, such as the moments. It's a way to describe a form when it comes to image data here, and when we have information about, let me say, the region, means you have the information about the pixel and its, let me say, neighbors. So, and there is another set of methods, which is the Fourier descriptors, and there are many types. And when it comes to local descriptors, which is the main focus of this paper, we can have the shape context, for example, the CIF descriptors and the CSS descriptors. So the paper from the title, it highlights that we are going to focus on the GCSS descriptor, which is standing for the Generalized Curvature Scale Space descriptor. And here, based on this table, there is a set of because, you know, in the state of the art, even in your own work, you need to study what exists, and you need to make kind of table or something to compare. There is a gap somewhere, and there is a good thing coming, or you need to cover that. For in this case, most of the measure to evaluate the descriptors is whether their invariance to Euclidean or affine transformation, their stability, their completeness, and their almost completeness is another property added. It's similar to the completeness, but as we cannot attend the completeness in the real world, because, you know, if when it comes to laptops, we deal with the discrete values, so we talk about the almost completeness. So here we will focus on the GCSS, but it's, let me say, belongs to the family of scale space methods, and it's a generalized version of the CSS, the curvature scale space descriptor. So why not CSS? Why GCSS? Because as we can see, the plus here, it's minus here. It provides this almost completeness property, as well as the stability and the invariance to Euclidean transformations. So based on this study, we are adopting the use of this descriptor. So we need to understand how it works briefly. So why I started with the journey of the dot to dot exercise in our first activity books in the kindergarten, for example, because that is the point. You always keep that in your brain. So we have the CSS descriptor. The idea of the problem is how to describe a shape. The idea of this is to have that shape in different scales, okay? And when I say different scales, means I'm going to apply a Gaussian filter to the input, like here, I have this contour, and I'm applying a Gaussian kernel with standard deviation sigma is equal to 2. Then I will increase this sigma value for 8, 16, 32, 64, for example, until I'm going to lose all the details of this like initial shape. But the main thing is gonna be there. There are 2 points that having the highest curvature value. They're going to stay because they describe the shape the most. It's like you are like getting fat through time, and through time the details of your body are lost. But the main points, your head is there and your feet is there. If you don't understand something, please let me know. Is it clear? Is it clear, please? Okay. So, how to extract now the points? Okay, what we do here is the smoothing the curve over time, but it's one step. Now for each scale or for each sigma value, we are going to extract the points that are going to be the helping in shape description. So at each point, we are going to extract what we call the inflection point. And this point is defined where there is a like, we are moving from positive to negative or from negative to positive for the kappa values. And given these points, for example, we are extracting as kappa like maximum points. It's already the points with maximum value are the invariant descriptors. So as this, for example, for the case of the shape, these points are the descriptors of this shape because they are the inflection points describing the shape. Now, in this case, we are only taking the maximum values. We are, for example, having a shape. We are applying smoothing with the Gaussian kernel. So we have the filtered contour, and here the variation of the curvature. What we take is that the maximum values after thresholding, for example, and just that are the descriptors. This is the CSS until here. If we are talking about generalized version, we are considering also the points which are having equal values as the maxima. So they are also important. That is why we have a representation with a set of points which are more near. We have focus on the points where the curvature value is really high. So this is the description. Here I am mentioning a visual difference between the CSS and GCSS descriptor. A CSS only considering one value of the maxima here. That is why we have fewer points. This one, it's having more points because it considers the neighbors of that interest point with the maxima. So we have a more rich representation. So in this paper, given a contour, we know very well which points are going to represent the contour, and they are called the GCSS descriptors, which are like complete, they are invariant to noise, to they are also robust. So what we will do here is that we will keep in mind that this is a typical way of extracting features. So it's handcrafted and manually done. So when it comes down now, for example, I am extracting this set of points. I want to classify who is saying this is a bone. It's me telling you it's a bone, and it's you are seeing it as a bone. It's a human classifier now speaking, but I need some algorithm to classify this. So moving now to the state of the art, when it's talking about the part for classifiers. So here we have the classical approaches and the approaches that are based on deep learning. As per the classical approaches, I am summarizing here, as well as I'm mentioning the deep learning one. So this is a general like representation. Given contour data, we say raw data, there is no like feature extractions. There is no interest points I'm taking. So here I could classify that given any machine learning algorithm, including the neural network. Or I can extract features, as I was showing right now, that red points, and I can also classify that with the machine learning algorithm. Or I may use typical like distances or correlation metrics, and also I can not start from the raw data. I can straight move from the feature and data, and then I may choose to do that with the machine learning algorithm. So this is a general map, but now let's start with the classical approach where we will focus on two types. If, for example, I have the set of statistical classification metrics or methods, I may be based on metrics, and metrics such as the dynamic time warping distance. This is a type of distance, as there is also the Euclidean distance that maybe you are more familiar with. So the Euclidean distance, if I have, for example, two like here, for example, I have two representation of a contour, and I have the same number of interest points, the same number of points. So here I can compare or measure the distance, let me say, point by point, because I have exactly the same number. So here it's a use case of the Euclidean distance. But if I don't have the same length of the like input, I have two input, like the green one and the red one, with different like lengths. So here I may need the dynamic time warping distance, which uses a different mechanism. So this, when it comes to classical approaches, they measure the similarity between inputs, whether based on the raw representation of contour or based on the analytical descriptors. Like I was saying right now, I extract the interest points and I measure based on that. And the second, as I was explaining here before moving to the second part, this classical approach is different from deep learning one, because here, as an engineer, it's me who is extracting the red points. It's me who is checking how I may extract that, and it's me who is giving to the classifier. Otherwise, for deep learning algorithm, we in general give an input, and it's the headache of the network how to extract features. So this is the main difference. And when it comes to deep learning approaches for contour classification, it's really a fresh topic. And there is only one related work exploring that in 2021, which is the Contour CNN, a convolutional neural network for contour data classification. So this paper presents a deep learning architecture, CNN, convolutional neural network architecture. And this architecture is mainly represented here. So you can see it's inspired by the AlexNet famous architecture. So here we can say the AlexNet architecture on the right, the way they are assimilating that for this architecture on the left. There are circular convolutional layers, there are priority pooling layers, again, circular convolution priority pooling, circular convolution priority pooling, 3 times. Then we find the global average pooling layer and a typical fully connected neural network for the classification. So this is a typical architecture. The way it works in how it extracts the feature, you are giving a contour as input. They are going to randomly extract features to tell you this is a bone, this is a cat, this is a dog, or whatever. So the problem with this existing architecture, or most of the works when it comes to deep learning, and since we are interested in contours, so we are studying this one, So the limit is mainly the explainability of the architecture first, and second, the certification of the model itself. So let's explore together. When it comes to explainability, this paper does not address these problems because as humans, if we are extracting features, I say these red points, for example, where I am computing some value, there is a high curvature, and I'm giving you what instructions or what logic I am following as a human, and I am given after that to the classification algorithm that I know exactly how it works and how it's going to perform the classification. However, for the deep learning case, I don't do anything, and it's not explainable because I don't know even what the model is doing, but the magic is happening here, given the input. I don't know what's happening, but at the end it's saying to me, this is a bone, this is a car, I don't know how. So this is why we are addressing this problem of explainability, because as humans, we really need to understand how things happen. And so the input we have, and the feature extraction block of a deep learning model is a black box. So you may hear a lot about black box. It's because of this, because we do not come to explain what is happening inside, what these layers are doing, how they are working. Even someone will explain, it's not clear or it's not satisfying explanation. Anyways, so moving to the second problem, which is the limit of the existing approaches, at least this one, which is addressing the problem of contours, which is the certification. Because you know now that we are in like deep learning, as I shown in the first use cases, it's almost everywhere. So somehow it's there in the safety critical areas. So it's, for example, in the autonomous driving, we have a car collecting like images from sensors we are having, and then we need to take the decision based on that input coming to the network. As the network is a black box, the input, we can have attacks or perturbations of the input. For example, here we have the same image, the same way, and the same, everything is the same. The only difference between these two images is the luminosity. So we call this an attack of luminosity, and which can lead the network to take a completely catastrophic decision. Instead of saying turn to the right, because of this change of the luminosity, it's taking another decision to tell you go left or go right instead of going left. So this is a problem, and we need to address this, because in general, when it comes to deep learning models, how they do the evaluation, as I shown you in the first table, they say this has the best performance because we have the best accuracy of the model. But it has been proven that the accuracy of a model is not a measure of its robustness. It's not enough to have a model, have this model, for example, it may have 100% accuracy. You give in the test data some input, which is with a little perturbation, and it takes a completely catastrophic decision. It can only mean that this network is not robust enough to take such decisions. So here we are also like addressing the gap in the certification of these networks. So this gap actually has been studied in a separate paper, because as most of deep learning models, they are for image data, for multi-dimensional vectors, for video, for speech data, and so on. It has not been like addressed this problem of certification in the case of contour, which is really from the motivation we see that it could be used in really like interesting points, fields, excuse me. So what we did here, that we are using another paper. I may go quickly through this paper, which is the ContourVerifier paper, representing like a way to evaluate the robustness of deep contour classifiers. So this robustness is already existing in the case of image. How it works, how I'm going to evaluate if I have a neural network which is composed of multiple layers. So these are different layers that present the neuron values per layer. If I have the input, how I can like certify or measure the robustness of the output. In this case, in general, we have an image, one image, and we have computed value of the different layers and one output. What they do in the literature that they use the idea of transformers in the concrete layers. And if I give the input with different versions of the input with different attacks, for example, one time I increase luminosity, then I decrease, and then I make some changes in the input or perturbations of the input. And at each time I would see what is happening inside of the model. I'm going to check that. So this is the idea of the transformers in the concrete layer. If I have this given a set of input representation, imagine a lot of perturbations, then I will have a lot of values. So these values may be represented in the abstract like representation, or we will have here the transformers in the abstract layer. So they may be like somehow moving in a domain, specific domain, to that input. So each time you have attacks, each time you have a domain in which the values, they vary from the minimum to maximum and so on. I wish this idea is clear because this is the abstract interpretation theory actually. So we are based on this. The model exists in the case of images data here. How it works, I have an input, and then I have that input. If you can see this 8 here, it's receiving different attacks, different perturbation. Then what I will have, it's a shape that abstracts all the possible perturbations. Then I will study, if I give this like domain to the convolutional layer of the model, what will be the shape of the domain as an output, and so on. So this is what I study. I study these transformations to the domain, and after all, I know that the green hair box represents where I expect my label to be. This is the domain presenting the 8th label. If me given all the attacks and all the perturbations still inside of that domain, it means this is guaranteed, it's verified, okay? If not, I'm coming out. So I can say here, oh, sorry, this model is not robust because it does not guarantee you a robust behavior. It does not guarantee you that this always will be classified as an 8. So this like framework exists, and the code for this, it's called Iran. So it's the ETH-Zurich robustness analyzer for neural networks introduced by the ETH-Zurich laboratory. So it's available in this link. What we did at that work, so we are adapting that to the contour information. We are studying the abstract domains after each layer of the neural network for the case of contours, and in order to certify that. So simply, just to simplify things, because of this paper, it's like studying the robustness of the introduced model. This is why I wanted to let you know how it was measured. So it was measured thanks to the ContourVerifier, which is a system inspired by Iran's system, but it's adapted to contour information. Here we need the concrete domain and which like variation, which perturbations, which attacks this input is going to have, rotation, translation, or whatever. And given the attacks, we extract an abstract domain. So here in blue, you can see an example of abstract domains. For example, in the case of translation, I know that whatever translation attack, I will be moving somewhere here in this domain. In the case of rotation, I will be somehow here. So we extract this domain and feed it with a set of neural network models. We feed it to this verifier, and it computes the value of the robustness, which is given by the number of the verified contours divided by the number of the well-classified contours. So this is a summary how it works and how we did this. This paper in particular shows the importance of robustness metric. And as I was saying in the start, it shows an example. As you can see, for example, here, we have in blue the accuracy and in orange the robustness. Sometimes you have a very, very high accuracy, but contradiction, you have a very low robustness. It means that even that the model is performed given the training data, if you give it an input which it has already been seen in the training data, just with an attack, it may give a wrong class. So this is the idea. That is why we cannot trust accuracy only as a metric. We need to study the robustness of model. We can't trust a model and may deploy it in a safety critical domain only if it has high accuracy and high robustness. So in this paper, so we are going to discuss the second now. Once done with the related works, we are going to move to the third section in the paper, which is the proposed model. So in this paper, you can see an architecture for the proposed model. But before that, which is given by figure 1 in the PDF I was sharing with you. But before that, I want just to explain again the difference between the typical convolutional neural network, means the existing state-of-the-art set of deep convolutional classifiers, and this one. In this paper, we show the possibility of customizing the features extracted by the feature extraction layers of a CNN model. So in typical cases, I told you that a deep neural network is composed of different layers. So you can see this is the first layer, this is the second layer, this is the third layer, fourth and fifth layer. So here we have a model. Do not need to understand in details. The model gets an input, and how it works, it convolves this input with some kernels. And in typical how it works, these kernels are initialized randomly. So these are random kernels. So you may, if you will use, or if you may use deep learning, you may train your model and find 99% accuracy. Then you go sleep. Tomorrow you have a meeting with your professor. You will repeat the training process. You are telling to everyone in the class, I'm getting 99%. Then when it comes in front of your colleagues, you are showing the results, it's only showing, let me say, 98%. So this difference in the output accuracy may be due to the kernels, that each time, whenever you repeat the training, you will have a new random kernels. And this is why how we can explain that. And these random kernels, when we convert them with the contour that we can explain, this is a bone. The output is something here that I cannot understand. Sometimes it shows you a line, sometimes it shows you nothing, maybe a dot somewhere that we cannot see here. So this representation, it's not a real description of the shape. So if we are offering the possibility of customizing these random layers, it means that I am setting the weights, or I am fixing them to something that I can explain as a human. So here we are setting them in this paper. We are showing for a visual representation that it's possible to set them to Gaussian kernels, and hence you are going to obtain the shape smoothed in different scales, as we were seeing in the start. So when it comes to the state-of-the-art part, this has been done. You can write a code how to smooth like a shape. Even ChatGPT you can give and he can write for you in any programming language you want. You want to do that in MATLAB, you want to do that in Python, it's gonna be a set of lines, and that is it. But here, when we say that we are performing this like smoothing process of the curve, it's not with the typical coding, it's with the neural network layers. We are using the layers for programming this, and this is the huge or the main difference, that we do not perform anything out of the model. We are using the model to do such like computations. So the architecture now is this one. So we have the initial contour. We have the arc length parameterization in order to have the contour represented with a set of points. I will go through this later. Then we have the typical GCSS existing one, statistical or analytical descriptor, that is given by a set of steps for different sigma values we have seen so far. We have, hello? Okay, I have another meeting. Sorry. So, are you here? Is it clear, please? So what we have here is the typical GCSS descriptor. How it works is going to smooth the curves for different scales. It's going to extract the maximum, like the maximum and minimum global points, and then that points having the same value we are going to consider. We can program this within the network layers. How to extract, to perform the convolution and extract the extremums. Typically, it's done like this, but in this DeepGCSS model, we do that using the convolutional and customized layers. We use the typical convolutions by setting the weights to be the first and second derivatives of the Gaussian kernels to have some like equations that may be needed for computing the kappa values. K here for the kappa, which explains the curvature values for each point. So after that, we take the maximum of that curvature points thanks to the max pooling layers. So everything which was typically done in like typical coding with the engineer, now it's done with the new way of representing the feature extraction block of a neural network. So we are personalizing this for the different like sigma or scales, and we are feeding to the concatenate all that, flattening, and then giving to the network for the classification. So we are introducing a novel deep learning architecture which imitates the way that the typical analytical GCSS descriptor works, but with no need for programming anything. It's the neural network which is extracting the specific features instead of that random features, unexplainable features that they were extracted before. Before, we do not understand what is happening. Now we can understand that this layer is computing this layer is having this mathematical equation, this layer is doing this. So as humans, we can understand at each step of the learning like process what is exactly happening in the feature extraction block. Now, this is a visual representation of the output of this feature extraction block. So the points here, the diameter of these circles, it represents the high value. So here you can see this is a high value of curvature, this is a high value, this is a high value, and here. So from these points, it can show you based on these points, I'm learning that this is a dog. Based on these points, I'm learning this is a bat, and so on. So this is how we are customizing the feature extraction block to be explainable, so we can understand and explain what features are extracted. And also we are like moving now to the experiments and results, where we are evaluating as well the robustness and accuracy of this model, given two data sets. The first one is the MPEG-7 data sets, which is a set of shapes data set extracted from these images. So we extract contours, and we have 70 types of objects, 20 different shapes for every object, and a total of 1,400 shapes. And also, this is a relatively, let me say, small data set. We are testing also for a bigger data set with 70,000 shapes, which is the MNIST famous data set, which represents digits from 0 to 9. And so we have 10 types of objects with 7,000 different shapes for a total of 70,000. And for the representation, once now here we are extracting the contour, we need to represent with the dots, with a set of dots. Here we are using the arc length parameterization. I'm not going to go through the mathematical equations and all, but this arc length parameterization, also called Euclidean representation, and it represents the shape with equidistant points, a set of equidistant points. So all these points are equidistant given the Euclidean distance. And when it comes to the evaluation for MPEG-7, we are measuring the top 1 and top 5 accuracy of the model. For we are having here for the training data set, we have top 1 for 98.98%, for the top 5 100%, and when it comes to the test data set, we have for the top 1 how much, 68.57, and for the top 5 we have 82.14. So mainly it has a good performance, but if we focus on the 68 or let me say 69% here, it's not bad, but the data set, MPEG set, as I was saying, has a little size. So it's a relatively small data set. Add to that, it has 20 objects. If we compare it to MNIST, which has only 10 objects, so it's double, that is why. Otherwise, here we have the comparative with the different analytical methods. So we have, these are points extracted with the CSS. They are not that much like, they are not almost complete. From these, we can reconstruct the shape because they are almost complete, which represent the GCSS, the analytical one. And here is our DeepGCSS, which is extracting mainly the same points of the GCSS because it's mainly imitating that through the deep learning layers. So when we compare that to the other like state-of-the-art analytical methods, we also find that 68% is not that much bad. It's not bad at all, but if we compare it, it's better than others, but still we have other like methods which are better. The only point here is that here deep learning techniques mainly need more data to prove that the accuracy of your model, and also the nature of contours in this dataset are different. So we may do again the experiments given the bigger data set, which is MNIST, and here we represent that in two cases. The first one in the case is the case of our model DeepGCSS with the custom, let me say, kernels which are explainable and so on. Here the kernels are given by the first, second derivatives, and they have mathematical equations detailed in the paper. We compare that to the typical case, what if I don't do anything? What if I don't custom anything? What if I don't set any layers? So that is the DeepGCSS in the case of random weights. And here we can find that the performance of the model when it comes to the accuracy, it increases like, it's like 97.20%. And we have also a good, nice plots of the loss as well. And for the validation accuracy, we have 95.15%, which is a very good and competitive accuracy. However, when it comes to the random case, means sometimes if you set the weights of your model, you obtain the nice plots. If you do not set and you have the same model, this can result in an overfitting, which is clear from these plots. We have a gap here, for example, between the validation and the accuracy for the train and the test or validation. And here you can see that this curve is like, it's like overfitting. So moving now to the other comparison we did with given deep learning architecture, we didn't only compare given based on the accuracy, we also compared it based on the number of the parameters. So this model presents completely very less like number of parameters than others, and also the number of epochs is less with the competitive accuracy. So this is the paper, and when it comes to the robustness, we were performing the robustness given the ContourVerifier. And so here we found we tested that or given a set of models from fully connected to convolutional models, and we found that the DeepGCSS model here in blue, cyan, sorry, it's like has a good accuracy of 80% for translation attack in the interval of 0 and 0.5. 0.5. As a conclusion, so this paper presents DeepGCSS, which stands as a significant advancement in the contour classification, achieving a delicate balance between interpretability and computational efficiency. So it integrates the GCSS descriptors within the architecture, deep learning architecture, in order to extract explainable and robust invariants, which are the GCSS descriptors, and which offers a mathematically explainable or expressible and transparent feature extraction process. So here I am finishing my presentation, and if you have any questions, just let me know. Any questions, please? Hello. Clear. Okay. If anyone is having questions, please let me know. Okay. Anyways, also I'm sharing with you my email here in the chat. So if you need anything, or if you may now with a clear idea what this paper is about, if you may have any question, you can send me an email at any time and we can discuss that. If you may think of using deep learning when it combined with software engineering, you can do that. If you need my expertise or you have any question how to do things, you can send me an email anytime. Yeah. So if you don't have any questions, I believe that we are done. If you have any question, you are most welcome now or whenever you want. Yeah. Yes, Lisa.
I just had a quick question. Thank you so much for your lecture. I was wondering, how do you see this model being applied to industry? Like, where do you think your first use case may be?
Yes, actually, there are two main use cases for this model, and we started working in this for a real world scenario. If I may go back to the slides quickly, and as I was explaining for you, we can use it. The importance of contour information could be whether in for example, biometric security here I was showing you, or also for the case of skin cancer. So for now we are applying that to skin cancer classification, because this descriptor that I'm talking about, the GCSS, it focuses on computing the curvature value, which is a very significant descriptor of shape. So here, how you can distinguish between if one skin cancer lesion is malignant or benign, if it has that much high variation of the in the contour. So you can say, so it's a benign, otherwise it's malignant. So in this case, if we have a typical CNN model, it won't focus with this specific point. You understand? If we guide the model to extract the specific invariant, so it is going to solve such or address such use cases directly. So we are working on this for now with our research group. And there is another use case that may be applied is if you have, for example, a car and you have images coming from everywhere, you can use this contour classifier and use it as an integrative model, because the visual information is not enough, and you can focus on image classification as well as the contours, and then to, let me say, to ensure a more robust model. So we are also working on this. I have one work published on this, and we are now with our research laboratory at UM Flint working at the skin classification problem.
Very interesting. One follow-up question. Would you say that this is computationally light in comparison to traditional models, since you can look at both the contour as well as the standard array?
Yeah, Actually, the thing is that here, if we are using this contour information, as I was saying, it's a fresh topic. When it comes to deep learning model, it's not like explored yet that much. Even if it's
Right.
explored, as I was explaining, it's explored given black box models, not
Mm.
white box models. So this one we are introducing is a white box. It will let you set what invariant, and it will give you the hand to decide the behavior of the deep learning model, because random behavior is not always a good option. And even if you are dealing with images, you can set your invariants to be a descriptor of image. In this case, we are choosing a contour descriptor, but you can, I have seen some works focusing with the SIF descriptor, for example, for explainability purpose. If you are dealing with code, you can have somehow what is the main important information in a code that I need to highlight. So you can help, let me say, your model by injecting this important information. Yeah, this is what I
Understood. Thank you.
welcome. Yeah, so any other questions? Please do not hesitate to ask any question. Otherwise, I believe we are coming at the end of our class. So thank you very much. And as I'm sharing my email with you, so do not hesitate to send me if you have any questions at any time. Okay, bye-bye.
Thank you. Bye.
Bye.